Okay, so without further delay, it's my pleasure to introduce Tobias Fritz from University of Innsbruck, who will give a talk on separation theorems and spectra for pre-ordered semirings with applications to tensors.
Okay,
Please.
yeah, thanks so much. So it's great to be here, and a kind of surprisingly large audience. At least I'm a little surprised that there's so many people kind of participating in this project. So I guess this topic is a little different from the topics otherwise. So please, and I'm a little uncertain as to sort of what a typical person's background is. Oh, is it too loud? Sorry, yeah.
It's okay, just go.
So at any time, please, feel free to interrupt me, and I'll try to kind of pay a little bit of attention to people's reactions, and then I can kind of try to adjust things to that. Okay, so let me motivate the whole topic by something that comes from tensors, namely matrix multiplication, and in particular, kind of more of a computer science question, the complexity of matrix multiplication, just maybe to get a bit of an idea of what people know. Who has seen this question before, the complexity of matrix multiplication? That's basically almost everyone. Yeah, that's great. Okay, yeah, good, thanks. All right, then I can kind of go through this quickly, I suppose. Right, the question is, how difficult is it to multiply two n by n matrices? And well, what do we mean by difficult? So of course, to make it mathematically precise, we should say what this means. And maybe in contrast to the kind of complexity definition that is most used, maybe mostly used in computer science, like for Turing machines, that kind of thing. It's a little different in that one just counts the number of multiplications. The idea being that the multiplications are the expensive thing, and addition is so cheap and easy to do that we don't need to bother with it. Okay, and then of course the naive algorithm, where you just take the definition of matrix multiplication or the usual formula, use that as your algorithm, has n cubed multiplications, right? But maybe we can try to reduce that, and indeed, and this is at least maybe quite surprising, or at least this was to me the first time I've seen this, that you can actually do better in n cubed. You can decrease this exponent, and so Straussen's famous algorithm has about an exponent of about 2.81. And yeah, this has been pushed quite a lot further, and I suppose now also probably many of you know about this, or maybe even some of you have worked on this. And yeah, this seems to be what the most recent record is. But I also should probably add, I personally basically don't know anything about these things, but I know more about some of the abstract theory behind why there exists such an exponent, and how to kind of characterize it in more abstract terms, and that's what I'm going to get to. Okay, so then I suppose many of you have seen this already, just to get a rough idea of how it's possible to have an exponent less strictly below 3. And so here is the idea for, or the equations for multiplying 2 by 2 matrices. Naively, 2 by 2 matrices, you would need 2 to the 3, right, n to the 3, so 8 multiplications. But Straussen's discovery is that it is possible to do it with only 7 multiplications if you just use suitably clever linear combinations of things. And now, well then, as you probably know, this is related to tensor rank. It's kind of the same thing, right? When you have a tensor, you want to write it, you kind of want to find clever, or suppose you want to determine its rank. That means you need to find clever linear combinations of elementary or of elements in the individual tensor factor spaces in order to write the whole thing as a linear combination of elementary tensors. And so it's kind of this is exactly the type of problem that we're dealing with here. And so to now make this a bit more formal, and also to actually state the abstract characterization theorem that I had mentioned. So this is what Strassen had proven in terms of what he called the asymptotic spectrum of tensors. So yeah, this gives a kind of formula for the complexity, and maybe before we go through this, let me maybe just mention that, of course, getting upper bounds in omega is kind of easy, right? In the sense that you just kind of try to find decompositions like this, try to find formulas like this. You can kind of enumerate all possible candidates, and so in this sense, this is a kind of tractable problem. It's kind of recursive. But finding lower bounds on the complexity, right? What is the optimal exponent? And find lower bounds on that, that's the difficult part. And this is, in a sense, what Strassen has solved. Yeah, at least or at least he reduced it to another problem. And he has a kind of separation theorem of which this bound is an instance. So, right, you can think of it as in a separation theorem, kind of like the Hahn-Banach theorem. The Hahn-Banach theorem would kind of witness when you have a point in an ordered vector space or something, it could witness the non-membership of a point in the positive cone. This is analogous to finding a lower bound here. If you think of the cone as sort of something like just the set of achievable things, then we want to witness non-membership, and that corresponds to finding a lower bound. And so in that sense, what we need is a separation theorem. And so this is what Strassen has provided. And so he showed that the optimal exponent, which is then the complexity of matrix multiplication, can be written like this, where this supremum ranges over these kind of invariants of tensors. Right? And think of invariant in the sense of the rank is an invariant of a tensor, right? It's something that is basis independent, and it's a numerical quantity, and Strassen's invariants need to satisfy very special properties. So they need to be additive under direct sum, should be multiplicative under tensoring, and monotone under restriction. Well, okay, so here I formulated this not for using language of bilinear maps rather than tensors, but I suppose it's clear how to, does everyone know how to, in what sense this is interchangeable? I guess so, right? I mean, yeah, just take dual spaces then to move the two factors on the left-hand side, the arguments of the bilinear map to the right, and then it's a tensor matrix multiplication tensor that kind of has these, is in a tensor product of 3 vector spaces. Okay, and for such tensors, we can direct sum them, and then, or bilinear maps, we can direct sum them, we can tensor them, and that gives us new bilinear maps, and new, yeah. And monotone under restriction is a condition that takes this form. Well, so what does restriction mean? Restriction basically is supposed to be saying you can get one bilinear map from another one. And by what getting it from should mean is basically this diagram, that you can apply some transformation to the vector spaces that form the arguments of the bilinear map, and also some transformation on the output in order to kind of simulate one from the other. So I find it helpful to kind of think of this in really kind of computer sciencey terms, in the sense that when you're given the beta, you can use that as something like an oracle or a Turing machine in order to simulate the alpha, and the f's are kind of the way specify how that simulation works, right? Because then you can say, well, if I'm given arguments, if I'm given elements of v1 and v2, I can use sort of the f1, f, and f2 as a kind of encoding, then feed that to my oracle beta, then beta produces an output in W3, and then I kind of decode that using F3 in order to get my desired element in V3. And so in this sense, this does the kind of simulation. If that produces the alpha I want, then that's the kind of simulation. Yeah.
Sorry, so F1 goes from...
Oh, sorry, yes, yeah, typo, yeah. The F1 and F2, the diagram is correct, and above there it's the wrong way around. Yes, thanks a lot, yeah. Yep. No, so this is the definition of when alpha less than or equal beta holds. But of course, you can have cases where it holds in both directions. But typically, it will not hold, and it will only hold in one direction, typically. Does that make sense?
Yes, but
yeah, right. Just, well, okay, just maybe for a trivial example, take alpha to be the zero map. And then you can get this, then this holds for any beta. But of course, typically, it will not hold. Well, for any non-zero beta, it will not hold the other way around. Just to kind of maybe the most trivial example. But also, I mean, the rank, if you think of this in terms of tensor rank, the rank is monotone under restriction. So alpha less than or equal beta necessitates that the rank of alpha should be less than or equal to the rank of beta, otherwise it cannot hold. Yeah.
This theorem of Konstanz you had on the previous slide,
Mm-hmm.
it shows that in a way we can just study 2x2 matrix multiplication to find out omega?
No, I would say no, because these phi, these tensor invariants phi, still need to be defined. These are assumed to be defined for all tensors of any dimension, with tensor factors, vector spaces of any finite dimension.
In the end, you drive them into 2x2.
Yes. So exactly, we evaluate all these invariants on just that matrix multiplication tensor, or bilinear map, but they need to be defined on all tensors. And that is, in a sense, the difficulty, I guess. So that one thing that we can, to give some, so I think I have this on a later slide. No, actually I don't. What are some examples of such phis? Well, if you take this from the tensor perspective, or if you write this in terms of tensors, then I think maybe I should just leave this to Matthias and leave this for the next talk, because he will know this stuff a lot better than me. So yeah, Matthias and co-authors found, as far as I understand, the first such phi that is defined, that works for all ground fields K, and is kind of non-trivial in the sense it's not just given by asymptotic tensor rank or something like that. Right. Not for all fields. Oh, yeah. Okay. Thanks. Yeah. Okay. Mm-hmm. Yeah.
But ranks of flattenings are the easy examples. Right?
Ranks of flattenings are the easy examples.
Yeah. Right. Yeah. Mm-hmm. Thanks. Sorry.
The multiplicative of the tensor product
Mm-hmm.
is Kronecker product.
I mean, it basically means that when you have, I can maybe just, let me explain it then in my terms, or in the language that I would use. It's, if you have alpha and beta bilinear maps like this, then alpha tensor beta would be a bilinear map on V1 tensor W1 and V2 tensor W2 to V3 tensor W3. And defined in the obvious way using multiplication and then extension to the tensor product, linear extension, bilinear extension. Okay, yeah?
If you want to recover the usual definition of the omega as an asymptotic tensor rank,
Mm-hmm.
how would you choose phi?
Then what?
Like, there's probably for some special phi you can write it as an asymptotic
No, so the asymptotic tensor rank, that's basically, if you want, that's the definition of omega, whereas this is the non-trivial characterization of omega. Right, this is Straussen's theorem. What you are interested in when you want to determine a complexity of multiplication, matrix multiplication, is asymptotic tensor rank. And then Straussen proved that it can be characterized like this. So what he proved is really a characterization of asymptotic tensor rank. And then one just observes that this corresponds to the complexity of matrix multiplication. I'm not sure if that answers the question.
But please notice that there's additive and multiplicative here. It's not like sub-additive or sub-multiplicative.
Yeah.
It's very strong.
Yes, exactly, yeah. I mean, if you write it as sub-additive and sub-multiplicative, I suppose then it's a much easier, then it could be a fairly trivial result. But yeah, this is really, in a sense, the class of all these phi's is so small that it's really hard to write down concrete examples. But it seems like the space of all these phi's is kind of not well understood. But yeah, I think we have to refer to Matthias for more on this. Okay, so now let's look at what is the kind of conceptual structure of this problem. What's going on here? And this, then, based on that, I will state actually what the general theorem that Straussen proved, and then my further generalization of it. Okay, so the idea is, and this is not really specific to bilinear maps or tensors, but this applies to many kinds of mathematical structures, right? That we have a concept of direct sum, and we have a concept of tensor product. And usually, up to isomorphism, the tensor product distributes over the direct sum. And so this means when we take isomorphism classes, we have what's called a semiring, right? Meaning it's like a ring, but we do not require existence of additive inverses. Otherwise, it's just like, and we typically have neutral elements corresponding to the zero thing, zero object, and then a kind of unit object. And so this is just like a ring, except that we don't have additive inverses. And so we can even use, well, this applies to the case of bilinear maps, right? If you take isomorphism classes of bilinear maps, where the dimension is not fixed. But the dimension itself, we allow all bilinear maps defined on finite dimensional vector spaces. So it's a bit maybe like categorical in spirit, except that we're not doing category theory, but we're looking at all objects at the same time as well, right? And then these form, isomorphism classes of these form a semiring under direct sum and tensor product. For example, with the neutral element, the unit element 1 is the multiplication map on K, right? Because that's the bilinear map that when you tensor with, you get up to isomorphism, just the bilinear map you started with. And now we can look at things like, well, taking kind of sums of this one with itself, and this way we kind of get natural numbers inside the semiring. And these sums are, well, if you just think about it a little bit, it's not hard to see that these natural numbers are just the multiplication maps, or are represented by multiplication maps on the k to the n's, just using, component-wise multiplication. Okay, is this sensible so far? Yeah. Yes, and here I'm kind of using, so I want to, maybe it's a little bit confusing, but I'm kind of mixing notation of, usual arithmetic notation for the semiring, but semantically, or really this is interpreted as direct sum, or the dot as tensor product. Okay, So then let's look at, also this is not just a semiring, but it's actually a pre-ordered semiring where we have this restriction. And what pre-ordered semiring means is that both addition and multiplication are monotone maps. Right, so if we have an inequality like this, if alpha is a restriction of beta, well then for any gamma, also alpha plus gamma is a restriction of beta plus gamma. That's pretty straightforward. And alpha times or tensor gamma is a restriction of beta tensor gamma. So in this sense, we got a pre-ordered semiring. And this is the abstract structure that we're dealing with. Okay, but it turns out that it's actually a special kind of pre-ordered semiring. It satisfies a particularly nice kind of boundedness. It has particularly nice boundedness properties. Namely, every element is upper bounded by a natural number. And this is basically just saying that every bilinear map or every tensor has finite rank. Because what this restriction amounts to, well, if you translate it in tensor language, this corresponds precisely to saying that, well, you can write it as a linear combination of, at most, n summands of elementary tensors. Well, or maybe now in terms of bilinear maps, the multiplication map on K has rank 1. And so then the natural number 1 plus 1 plus 1 and so on has rank n. And so this is just saying that then you can reduce it to kind of the universal rank n thing, universal rank n bilinear map. Okay, so yeah, every element is upper bounded by a natural number, but also it's kind of lower bounded in a sense by a rational number if you want, in the sense that we can multiply, well, in a trivial way, I mean, every non-zero bilinear map is lower bounded by 1, because it has, well, it has rank at least 1, and this shows that you can basically simulate the multiplication of K using alpha, and so this is how we got the second inequality with m equals 1. But I wrote it in this form with general m because Strassen then also has this general theorem which says that, well, it's enough to have this weaker assumption. There exists an m for every alpha that satisfies this. And so the important point is that every alpha, in a sense, should be upper bounded and lower bounded by a rational number if you want. Okay, yeah, and this is going back now to the earlier question about asymptotic rank. What we're interested in the complexity of matrix multiplication is to find the smallest omega which satisfies this inequality for all sufficiently large n. So it's a sort of scaling that we want to. Right, so now n is not the matrix size anymore, but the matrix size is 2 to the n. Because on the right-hand side we have kind of the 2 by 2 matrix case, which is this 1 plus 1 element. And then we're taking nth tensor powers of that. So we're multiplying 2 to the n by 2 to the n matrices on the left. And on the right-hand side, we just have the, actually don't even know what it's called, you know, just the usual, the obvious tensor that has rank 2 to the omega n. Okay, yeah, then so the question is to find this omega. So basically this suggests we need to have some kind of separation theorem that involves large powers of semiring elements. And this is exactly the thing that Strassen proved. And I want to argue that this kind of theorem is actually very widely applicable. Because as I said earlier, every kind or many kinds of mathematical structure have a kind of direct sum and a kind of tensor. And there is a way to say that, well, one object is in a sense contained in another. And whenever you have a situation like this, it's very likely that some kind of theorem like this applies. Doesn't mean that it's going to be useful or tell you anything new. but at least it gives you maybe an abstract, gives you a kind of framework to think about things, and in some cases it will give you some pretty strong results. Okay, so yeah, here's Straussen's general theorem now about pre-ordered semirings. Yeah.
Did you tell us what is the power of some omega?
Power of some omega?
You need the floor on the previous slide.
Oh, thanks. Yes, of course. Yeah. I was a bit sloppy in a notation here, but here you can just take floor or ceiling or just round omega n to a natural number. Yeah, I didn't want to clear the notation. Thanks. Yeah. Okay, so yeah, here's the general separation theorem. These conditions, the two inequalities on top, are just what I had on the previous slide. Now I'm writing n for the natural numbers in S, meaning just this n-fold sum of one with itself. Right, so again, just this thing that every x should be upper and lower bounded kind of by n versus 1 over n, kind of morally speaking. And then we have here this chain of implications, and maybe start with the second one. The second one says that if kind of y asymptotically dominates x, now we're always looking at large powers, asymptotic in this sense, then it's kind of trivial to show that because phi preserves is multiplicative and phi is monotone, that we're going to get phi of x less than or equal to phi of y. But the first implication is the difficult one, and you know, as usual in separation theorems, this is the difficult one, that if you have a strict separation by some kind of family of witnesses, then you want to conclude that this also holds in the at the algebraic, and in some sense, there is also a kind of algebraic witness of that. And so, yeah, this is what Straussen proved. If you have strict inequality for all phi's, then we have this asymptotic inequality there in the original semiring. Okay, and yeah, based on that, you can. It's fairly easy to basically arrive at Straussen's formula if you kind of plug in these two things for x and y. And then you just optimize over omega. And use the fact that phi of 1 plus 1 is going to be 2, because phi is a homomorphism. Okay, this is maybe in a sense the key kind of ideal, so please interrupt if there's anything unclear about it. Yep. Mm-hmm.
Does there actually exist a negative alpha in this scenario?
No. So as soon as you have negative elements, or as soon as some elements have a kind of additive inverse, then the whole thing will necessarily collapse in the sense that all elements will become ordered in both directions with respect to 0. And this is kind of excluded by the assumptions here. So this is actually a kind of ordered semiring where no non-zero element can have an additive inverse. That's a consequence of the assumptions. Yeah, thanks. That's an interesting point. Okay. So I guess many of you are familiar with separation theorems or of different kinds, and maybe like positive Stellensatz, this kind of thing. Who actually works with so real algebra, positive Stellensatz, that kind of thing, sums of squares? That's okay. Yeah, not that many. So then let me try to make it brief. So in those cases, in that kind of setting, the standard or how those results are often used is that you're actually interested in geometric inequality, right? Let's say you're interested in is a polynomial non-negative or not. And this is kind of a question about non-negativity in a geometrical sense, right? Is it non-negative at every point? And then you try to witness that through algebraic certificates using sums of squares, this kind of thing, for example. But the applications that I'm talking about here kind of go the other way around, in the sense that here we are actually interested in, here the difficult thing is to conclude the algebraic certificate, which is the large power ordering. That's the difficult thing that we actually want to characterize. And what we can hold is easier, and I'll show examples where the other thing, evaluating the phi of x and phi of y, that's much easier. So it kind of goes the other way around. Yeah. Okay, so yeah, I kind of already hinted at this. Looking at a set of all these phi's itself could be an interesting thing, and it's a kind of spectrum. Right, it's in some sense we're looking at all ways of evaluating the semiring elements to numbers, and so this is a geometrical object, and so Strassen originally called it the asymptotic spectrum. But I'm going to try to argue in the next slide that that is a misleading terminology. And so I like calling it a test spectrum, because in a sense, well, we're just testing all the semiring elements, we're probing them by applying these monotone homomorphisms. Yeah, and if you just use kind of the obvious topology of pointwise convergence, it's not so hard to show, kind of using standard arguments, it's a compact Hausdorff space. Maybe you would also wonder, here we're only looking at real valued or R plus valued homomorphisms. This seems a little disanalogous to the spectrum of a commutative ring, because in a commutative ring, the spectrum elements can have any sort of residue field. And so maybe one would hope that also in this setting, there would be a general definition, a broader definition of spectrum like this, but I'm not sure what it would be. But maybe there is one, in which case I would expect this test spectrum to be a kind of subspace of that. Okay, yeah, I already said that for the bilinear maps, only a few things are known. And maybe another perspective on this kind of result, and why I don't want to call this as the spectrum asymptotic, is because it's analogous to, there is a sense in which it's still analogous to the spectrum of a commutative ring, and also to the Gelfand spectrum of a commutative Banach algebra. And if you look at the corresponding separation theorems in those contexts, those separation theorems are also asymptotic in precisely an analogous sense. And so since we don't call those spectrums asymptotic, and there is no other kind of non-asymptotic spectrum in those cases, I think we also should not call Strassen's spectrum asymptotic. Yeah, and so for example, for a commutative ring, one version, I guess, of the Nullstellensatz is that an element of a commutative ring is nilpotent if and only if it vanishes when you consider it as a function on the spectrum that takes values in residue fields. That function vanishes if and only if the ring element is nilpotent, right? So this is also a statement about large powers. And similarly, for the Gelfand spectrum, we have the spectral radius formula, which in this setting, in current notation, looks like this. It also characterizes the norm of large powers of an algebra element. So again, these things are also about large powers. Okay, now I want to turn to another application, and an application where we can really, where the spectrum, the test spectrum, is completely classified, and we really get some non-trivial results from this kind of thing. And the idea would be to look at representation theory, representations of a compact Lie group. So in that setting, again, we have a notion of direct sum, we have a notion of tensor product. We can say that one representation is included in another. So hence isomorphism classes form a pre-ordered semiring. And so this looks promising. Maybe we can apply Strassen's theorem, right? But recall that Strasson's theorem had this boundedness assumption there on top. And so we need to check if this actually holds before we can apply it. And so we should check what the natural numbers are in this semiring. Well, the unit element is just a one-dimensional trivial representation. And plus this direct sum. So what we get as the natural numbers are just all the trivial representations of all finite dimensions. So that's maybe not what we wanted, because now Strasson's condition does not hold. Because, well, it's obviously not the case that we can embed any finite dimensional representation into a trivial one. So that's maybe bad news. Strasson's separation theorem does not apply. So that means we need something else. Before I get to that, before I resolve that, maybe I can just say a little bit about or maybe I should basically skip this, but there's also a kind of more explicit description of what the semiring looks like in the case of SU2. And here one can see, for example, what happens with the ordering when we actually go to large power. So this is a semiring which is kind of generated by a variable x, which corresponds to the fundamental representation of SU2. And this is such that x is not contained in x in its third power, not less than or equal to its third power. But when you take the square on both sides, then it does hold. So again, here we see some kind of, that taking large powers gives you more ordering relations. This is kind of, in this semiring, the kind of simplest example of that phenomenon. Okay, so yeah, as I already said, we need a more general separation theorem, and I call these Vergleichstellensätze after Vergleichen to compare, because it's unlike a Nullstellensatz, it's not about where things vanish. Unlike positive Stellensätze, it's not about where things are positive or non-negative, but it's really about comparing elements, and so hence that terminology. Yeah, and so it turns out that there's a generalization of Strasson's theorem, Strasson's Vergleichstellensatz, which does apply, and this uses a weaker version of his boundedness condition, which looks like maybe it's just a mild weakening, but it's actually, you need completely different arguments to then do anything with it. And it's not, so Strasson's proof was a reduction to known kind of results, positive Stellensatz, but this one is not. Okay, so I now require that every element is just upper bounded by some power of a fixed element. That's called power universal, and similarly the other way around. And so Strasson's condition was saying that every element should be upper bounded and similarly lower bounded by a natural number, and so that corresponds to the case where this power universal element would be, for example, 2 or any natural number other than 0 and 1. Okay, and a nice example to keep in mind maybe is the tropical semiring, where we take still the non-negative reals with the usual multiplication, but now replace the addition by taking the maximum. If you've seen the tropical reals before, then maybe you've seen kind of the logarithmic version of this, where you take addition for multiplication and you take all the reals together with minus infinity. But I mean, those two just correspond under logarithm and exponential. And for my purposes, this version is more convenient. Okay, so yeah, here's the, yeah. Oh, sorry, what did I do now?
If you take the tropical semiring with multiplication, how is u equals 1 power universal?
Yeah, no, that's great. Yeah. Sorry, no, that is a typo. This should be 2. Thanks. Yeah. This was still, I had an earlier version of the slides where I had used the usual logarithmic version, and then I had changed it, and I guess I forgot to change this. So any number bigger than 1 is power universal, right? Because then just take a usual power and the usual ordering, then it dominates everything.
Sorry, I messed it up completely.
Oh, how does it go back to full screen? Oh, thanks. Yep, this, right? Oh, this one? Oh, no. Sorry, yeah. I don't use neither Windows nor Acrobat Reader at all, so I'm not. Oh, okay.
But that did not work.
Oh, it should be presentation mode, right? Not full screen. Yeah.
Sorry.
Here? Oh,
Yeah.
which one? Okay, great. Yeah, thanks. Thanks a lot. Okay, yeah, so then here's the analogous theorem. I've written it down here a little bit differently, just to, kind of, and also a slightly stronger formulation, just to maybe, present another formulation of what's more or less the same thing. So here your assumption, this is kind of the, except for the final sentence at the bottom, this is the difficult part, so the first implication from earlier, right? If, assume that we have two non-zero semiring elements, which are strictly ordered for every element phi of the spectrum, then we can conclude certain kind of asymptotic statements. Then we can conclude the existence of algebraic certificates. And there's three kinds of algebraic certificates. These are A, B, C. And maybe you can just look at them a little bit to parse what these algebraic certificates look like. And of course, the one that we're really interested in is C. This was going back to the matrix multiplication, complexity of that, and also maybe in a representation theory case. This is like maybe the thing we're most interested in. Yeah, and so yeah, as written down here, this can be concluded under the additional assumption that Y itself is a power universe element. Otherwise, you cannot expect it. Okay, and then at the bottom we have kind of the trivial implication that if any such algebraic certificate exists, so if, for example, these inequalities hold for any fixed n, or for any non-zero a, then of course we get phi of x less than or equal to phi of y just by applying phi and using the fact that every such phi is a monotone homomorphism. Okay, so of course this recovers Straussen's result, but I want to claim that this is substantially more general, and for example, it applies to the representation theory case. And also, I should point out that now the homomorphisms, in Straussen's case, they were homomorphisms to R+, but now we also need to look at monotone homomorphisms to the tropical reals. And now I think this is really an important, now we're at a point where this makes clear that we cannot reduce this to standard results like positive Sternsätze. Because when you try to do that, well, these homomorphisms do not extend to the ring that is generated by the semiring. Because, I mean, you cannot just work with additive and kind of formally adjoin additive inverses. They would just kill the tropical reals. Okay. What happened now? Oh. Not sure why it stopped working. Oh, okay, then maybe I just have to do it here at the laptop. Okay, so just a little bit about the proof. So the structure of the proof is kind of fairly standard, I would say, in the sense that you just kind of, in algebraic terms, you kind of weaken the ordering a little bit, then you go to some kind of total extension of it, and then you show that this corresponds to such a monotone homomorphism like in the theorem. But the details, the details are quite intricate, I would say. And so, for example, the proof involves this kind of weird, and admittedly, I still don't really understand this identity. I mean, I can prove it, but I'm not really sure what it means or how to really think of it. And involves this identity, and the only difference between the two sides of the equation is that inside the brackets, so the round brackets on each term, we have powers of x on the left-hand side, but we don't have those on the right-hand side. And so then maybe you think that it's a little odd that this equation holds because, well, when you just make a small change in an expression, typically you would expect to get something else, right? But here it indeed again turns out to be the same thing, and this plays a kind of an important role in the proof. And yeah, it involves a reduction to the semi-field case. This is maybe apparent already from in the equation, the fact that I'm assuming that x is an inverse, that I'm taking negative powers of x. So meaning that we can just kind of formally adjoin multiplicative inverses. This is something that turns out to be useful. And yeah, just to give an example of what these semi-fields can look like, just take, for example, continuous, strictly positive continuous functions on a compact Hausdorff space, and then you throw in the zero function as well, and then obviously these are closed under addition and multiplication, and contain a unit element, the constant 1 function, and every non-zero element has an inverse, right? A strictly positive function, you can just take the pointwise inverse, and then that's the inverse function. So this is an example of such a pre-ordered semi-field. Okay, and in a sense we're saying that all of these are kind of, as far as asymptotics are concerned, these are the paradigmatic examples of semi-fields. All other ones can embed into these. Okay, but yeah, and then another ingredient is what to my mind is kind of the fundamental theorem of pre-ordered semi-fields. This is kind of a result saying, which is again kind of analogous to many of results like in other areas where you say that when you have some kind of partially ordered algebraic structure, then you can kind of prove that a partial order can be extended to a total order, and in such a way that any sort of desired elements you want to separate can still be separated. And this is here precisely this result for pre-ordered semi-fields. So yeah, if we have, this does not even need the existence of power universal elements or anything like that. So I think this is really very widely applicable. And one can do a lot more with this, I hope. Although so far it's a little, not all that much has been done with it, other than deriving this kind of thing.
So that enters the proof of...
Yes, yeah, exactly. That's sort of the key part of the proof. So in the sense that this equation enters the proof of this, so that's kind of where most of the technical meat comes in, and the reduction to the semi-field case, that's kind of the more kind of boilerplate part of the proof, if you want. Okay. So just to illustrate maybe how pre-ordered semi-fields are special and what's nice about them, let me explain why the asymptotic, the large power ordering just degenerates if you have multiplicative inverses. So by showing that, for any natural number that is at least 1, such a large power ordering is actually equivalent to the plane ordering x less than or equal to y. Of course, from the left-hand side to the right-hand side is trivial, whereas from the right-hand side to the left-hand side, that's the surprising part. And here's basically the proof. For people like Matthias or anyone who studied some kind of quantum information theory, this is basically embezzlement. Okay. Yeah, and then of course, this is just kind of, I guess, straightforward verification, but then you just need to argue that also the sum is non-zero, but that's basically because we don't have any additive inverses, and any non-zero element adding non-zero elements gives you non-zero elements. That's basically what's going on here. Okay, now we saw this test spectrum in Strassen's theorem earlier, and here's the more general version. Now, in addition to the homomorphisms to R+, which is up there now covered by this additional thing, we also need to look at the homomorphisms to the tropical reals, right, as I said. And in a sense, these extra homomorphisms, these compactify the spectrum. Without these, you could get, I can give another example of this, if a more kind of simple example of this, if anyone is interested. I think I actually have it on the next slide. These compactify in many cases. You would get a non-compact space without these tropical ones, but if you take these into account, then that results in a compact space, and this maybe also explains why these are important as maybe an additional explanation for that. Okay, and for the topology of coinwise conversions, yeah, it's a bit more subtle how it needs to be defined. One cannot just look at a simple evaluations. Because the real and the tropical part kind of, you need to have them kind of interact in a nice way. Okay, but now this is maybe a bit too much detail for the purposes of this talk. Okay, so now here's just kind of the straightforward application to representation theory. And so I've done this for the case of SU2, just because in that case, the test spectrum can actually be explicitly determined. I mean, of course, the application works for any compact Lie group. That's not so hard to see, but it's hard to see what the test spectrum would be. And I'm still kind of, I'm kind of hoping that someone who knows more about representation theory than I do will be able to do it. So I've been able to do it to determine a spectrum in the case of SU2 based on some existing results, which I will show on the next slide. But yeah, so here's the theorem. If we have these inequalities, no, sorry, actually, okay, that explains why there's something missing. Okay, so yeah, let me skip this thing. This is a kind of polynomial semi-ring example, which just shows again how the tropical part kind of compactifies. Because in this case, the spectrum would be just the evaluation maps at any point on the positive axis, which is not compact, but then taking the degree gives you an additional tropical homomorphism, and this kind of compactifies the spectrum and corresponds to evaluation at infinity in a sense, because taking the degree corresponds to looking what happens at a polynomial when you plug in large values. Okay, now for the representation theory case, yeah, this is the slide that explains what a spectrum is. It turns out to involve so basically a particular spectrum element phi will assign a number to every finite dimensional representation, right? And these numbers have to be additive under direct sum, multiplicative under tensor product, and monotone under inclusion. And it turned out that these have actually been classified for, in a just unrelated context. There's a book by Semirings on functional equations on hypergroups, and that's where I found the classification of these. And this is what they look like. So x to the n is just the irreducible, SU2 has one irreducible representation in each dimension, right? And so these powers, x to the n is the irreducible representation of dimension n plus 1. And then the ANs are natural number coefficients that give you the decomposition of any representation into irreducibles and with their multiplicities AN. Yeah, and then this is what these homomorphisms look like, what a spectrum looks like. And it turns out to be very similar to the polynomial semiring. And there's one additional element that is analogous to taking the degree of a polynomial, and in the representation case, it's taking the highest weight. Just the maximum n that appears in decomposition into irreducibles. Okay, yeah, and then here we just get this. This is the corollary. This gives conditions under which one representation embeds into another one at a level of large powers, or at a level of tensoring with another one, and these are close to necessary and sufficient conditions. I was in the sense that so conditions A and B are sufficient if you have strict inequalities, and they're necessary with non-strict inequalities. Okay, now, so yeah, I should be wrapping up. So let me say a little bit about another application that or possible application that I've been briefly thinking about for the purposes of this talk, is that we can, I've explained the Strasson's application to bilinear maps or to tensors. We can do this for any number of tensor factors. And I've explain something about symmetry representations, an application where Strasson's theorem does not apply, but the generalization does. And also we can I think it should be possible to combine these two things and look at tensors that live in tensor products of representations. And then look at those and look at restrictions between those. I don't really have any sort of particular application for this in mind, but it would just be another case where Strasson's theorem does not apply, but yeah, the generalization does. And so yeah, take a bit more concretely any finite group G. I'm not sure how to do it for non-finite groups. And representations V1 to Vm, and then a tensor alpha in that. Then we can define restriction. A G invariant tensor, right? Where we just look at the induced action on the tensor product of these vector spaces, and we can define restriction in terms of the existence of intertwiners or G equivariant linear maps. And then again, we get a pre-ordered semiring. Again, Strasson's condition does not hold because the natural numbers inside the semiring just are about these carry the trivial representation. But as long as the group is finite, it looks like there is nevertheless a power universal element. And so this means that Strasson's version does not apply, but the generalization I've presented involving the homomorphisms to the tropical reals does apply, and then ends up looking like this, kind of just like Strasson's thing, but yeah, and analogous to Strasson's version, but now in a kind of G invariant equivariant version. Okay, yeah, that was it as far as I'm concerned.
Thank you very much.
Yep, thanks.
Are there first questions? Yes, please.
So if we go back to Strassen's 1986 theorem, is it actually possible to use that theorem to deduce some concrete numerical inequality on omega, like an upper bound or a lower bound? No? Okay. Thank you for the answer.
That sounds like more of a question for other people in the audience, so please.
Any question from the audience? Any answer? Sorry.
I guess it's just really hard to write down enough concrete elements of this to,
Yeah. I mean, we don't have any non-trivial lower bounds on omega.
So as
No, but we do have some upper bounds. But not obtain, so this is not useful, this hasn't proved useful to obtain any upper bound.
So as far as I know, maybe let me say that
Wait,
Strassen's version.
It's an equality.
In some sense, you may think so naturally every f or every function you exhibit will be an obstruction. Will be an obstruction to some asymptotic degeneration. So in principle, they should give you lower bounds. It's just that all of those lower bounds will not give you a better bound than 2. So all of the ones that we know. However, there is the most prominent method to obtain upper bounds on omega. They go via the laser method. And the laser method consists of 2 parts, where one of the parts is not about rank, but it's about asymptotic subrank. So it's about the distillation. So it's about the opposite, right? So it's like not like how big a unit tensor do you need to convert to your tensor, but how much unit tensor can you get out of your tensor? And for this, actually, these methods help. So you can, in fact, obtain lower bounds, maybe not unconditionally, but for the certain approaches that people use for obtaining upper bounds using such constructions. So whereas sort of plain the answer would be no, it is kind of conditionally yes. Okay, I can tell you later.
Yeah, thanks. So let me maybe just add a bit in a different direction. So personally, I'm interested in finding more examples of such pre-ordered semirings where one can completely determine the test spectrum, write down all the points explicitly. So I've done this for representations of SU2. I've done it for an application to random walks, asymptotics of random walks, and for asymptotics, I've done it with other people for asymptotics of matrix majorization. Never mind what that is, but my point now is just that there are a few cases, and I'd like to find more. So if anyone has any ideas, please let me know.
Let's, as we don't have much time, let's thank Tobias once more.